Hi, welcome to 12400, our Space Odyssey. I'm Professor Richard Binzel, and I'm giving the lecture today. And if you'll allow me just a few clicks, we'll get started. And here we go. Today, we're going to talk about the origin of the moon. And I've got several learning objectives. I'm going to tell you right up front what they are. The first is to understand why the origin of the moon for a very long time was an unsolved problem. And then try to explain what was the scientific breakthrough of the Apollo program that led to our understanding of where the moon came from. And to do that, we're going to take a little bit of an aside and learn a little bit about isotopic chemistry. The next thing that I hope you'll learn from this lecture is how the moon fits into the overall picture of planetary formation. That's a subject we've been talking about for several weeks now. And how does the moon fit in to the overall topic of planetary formation? And then finally, there's something really amazing about just looking up at the moon. And that's something I want you to appreciate. And we hope it's one of the kinds of things that you take away from this class and not just remember it next year, but remember it for the rest of your life. Pretty tall order. Let's keep going. All right, so we're in this kind of impersonal teaching mode. And I thought maybe to overcome that, just share a couple of personal asides with you. And the first is that I was just a kid with a telescope back in the 60s and early 70s, and I was fascinated by the moon. So today's lecture comes pretty naturally. And I grew up with a map of the moon on my bedroom wall. And I memorized looking at that map and looking at the moon through my telescope, literally hundreds and hundreds of craters and places on the moon. And I was influenced about the moon because of a book I read in first or second grade, one of the first books I could read all by myself, as the Cat in the Hat series suggests. And the title of the book was You Will Go to the Moon. It wasn't someday you might go to the moon. It was you will go to the moon. And just like everything you read on the internet is true, everything you read in a book must be true. I mean, that's what you think when you're a little kid. And so I was sure I was going to go to the moon. And so I actually, I always thought about going to a lunar base. I wanted to go be director of an observatory on the moon. And anyway, I had these visions of a lunar base with moon buggies and rocket ships and really pretty amazing stuff. So I actually applied to the Apollo program and was a finalist in 1990. And they ended up taking the other guy. And then I was re-invited back by the head of the program named Dwayne Ross to reapply in 1992. And I actually declined at that point because I had become so involved in teaching and so much enjoyed working with students at MIT that I thought that was really a better career for me because I didn't see the United States or any nation getting back and having a moon base, let alone a lunar observatory, anywhere in my career lifetime. And so that becomes the job in your career, is to be the one that gets to go to the moon and maybe be the director of the observatory there. So I didn't get to be an astronaut, but in a lot of the committee work and the review work that I've been doing for NASA over many, many years, I've gotten to meet many different astronauts over time. One of my favorites, of course, is Buzz Aldrin, everyone's favorite Buzz Aldrin, who I've gotten to meet several times and gotten to know a little bit. He's a strange character. But anyway, a little fun aside there for my time with Buzz. All right, so back to the moon here. This is a picture taken from a backyard in Colorado, and it forms the backdrop for some of the fundamental facts about the moon. So here's what we knew about the moon prior to Apollo. We knew that the density of the moon is less than the density of the Earth. The Earth's average density is about 5.2. For the moon, it's much less, about 3.3. We know the moon's, and so anyway, we know the basic density of the moon, basic characteristic of the moon. But we also know that the moon's orbit is really strange in many ways. For Jupiter, for example, the Galilean satellites of Jupiter orbit around Jupiter's equator. It makes perfect sense. But the moon does not orbit around Earth's equator. The moon orbits in nearly the same plane as the Earth's orbital plane around the sun. So the moon is going around the Earth, but the plane of that orbit is like the plane of the Earth's orbit around the sun. Well, in other words, it's tilted about 23 degrees compared to the equator of the Earth. And the moon is just slightly offset, slightly inclined to the ecliptic plane. And that's the reason why we don't get eclipses every time there's a new moon or a full moon. So the moon's orbit is strange, not what we would expect, and its composition is odd too. So the pre-Apollo hypotheses for how you form the moon came in three forms. One was that the moon was spun off the Earth by fission, basically a rapidly rotating Earth spun off material that made the moon. But that doesn't account for why the moon doesn't orbit around the Earth's equator. The angular momentum would have aligned the moon's orbit to put it in an equatorial orbital plane, and it's not. So, great hypothesis, but it doesn't match the facts. Second hypothesis is that the moon was another body that just formed kind of nearby the Earth, and they formed close enough that they became gravitationally bound to each other. But that doesn't explain why the moon would have such a different composition if they're kind of condensing out of the same stuff in this neighborhood of the planetary nebula. Then they should be very identical in composition all the way to the core, literally, and they're not. So binary accretion doesn't fit the data. And then maybe the moon kind of formed elsewhere, but then got to be captured by the Earth. But again, we know the solar nebula was pretty well mixed, and that the ingredients should not have been so different elsewhere to make a moon that had a different composition of the Earth. And so the capture hypothesis doesn't work very well either. So this is the framework that we went into the Apollo program. And one of the amazing scientific accomplishments of the Apollo program was bringing back samples of the moon, nearly 1,000 pounds of samples, nearly 400 kilograms of samples back to the Earth for detailed study in Earth's laboratories. And a breakthrough that came from studying these samples is that we found that the isotopic composition of moon rocks is the same isotopic composition as the Earth. We're going to spend some time looking at what this means and why this is so important. But in short summary, what this means is the isotopic compositions of moon rocks and Earth rocks means that they were born together. The Earth and the moon were born together, kind of like twins. So they have a common origin at the beginning of our solar system. Very incredible finding. But there's still an oddity. It turns out that the moon, in terms of its elemental abundances, in this case, it's how much magnesium, how much silicon, how much iron, things like that, atomic elements. The elemental composition of the moon matches the crust of the Earth, but not the overall composition of the Earth, because the moon is iron poor. Very little iron in the moon compared to the Earth. So that accounts for the density. So when we measured the lunar rocks, we now understood why the density was low. The moon just simply does not have very much iron. And so even though the Earth and moon may have been born together, They're not identical twins, they're fraternal twins or siblings. And so we got these new facts added to trying to understand where the moon came from. Now, I want to take a little bit of an aside, and it's worthwhile taking a little bit of an aside to talk about isotopic composition, because this is really important, really powerful in terms of understanding the chemistry of our solar system. So let me explain. So any rock, whether it's an Earth rock or a moon rock or a meteorite, we can measure its oxygen isotopes. And what this means, well, let me just show you what the isotopes are or remind you. The three main isotopes of oxygen are oxygen 16, which is basically what we breathe, oxygen 17, and oxygen 18. And you see in the percentages here, oxygen 16 is the most common form of oxygen. And the important thing about these oxygen isotopes is that they're stable. They basically have infinite half-lives. So the basic amount of these isotopes that were present in the Earth or present in the moon when they formed are there forever. And they're only changed in any given rock or any given sample based on how much that sample has been heated or melted over the course of its history. So this means that measuring oxygen isotopes is an incredibly powerful thing in terms of understanding or trying to read the record of what kind of heating and melting history any rock or any region of a planet has had. So you see, isotopic chemistry is a great tool for looking into the past. When we measure the isotopic chemistry, so for example, here's a measurement of a moon rock in terms of its isotopic oxygen isotopes. And we make a measure and we plot it in a graph. Let me tell you what these graphs mean of oxygen isotopes. Basically, there are two parameters that we plot. On the x-axis on the y-axis is what we call delta 17, delta oxygen 17. And what this is it's all measured in ratios, and it's how does the ratio of oxygen 17 to oxygen 16 in that sample, how does it differ from some standard? And then delta 18 oxygen is the ratio for how the oxygen 18 isotope and its ratio to oxygen 16, how does it differ compared to some standard sample? And you'll see in the equation for these deltas that they're multiplied by 1,000%. So in other words, these isotopic differences are a few parts per thousand. They're very, very small. So isotopic chemistry is a very precise, very delicate endeavor, but it's a huge field in planetary science and in Earth science for measuring histories of our worlds. Okay, so we measure these oxygen isotopes relative to some standard, and it's kind of fun because the standard that we measure relative to is something called Vienna Standard Mean Ocean Water, or VSMAO. And what VSMAO is basically a kettle of ocean water stored in Vienna. That is just sort of the fundamental reference. And it's great because ocean water is something that's readily accessible, but there's very specific ocean water is what we measure as our absolute reference in oxygen isotope chemistry. And it's just like there's a meter stick in Paris and a standard kilogram also in Paris, that are historically have been the standards for measurement. This sample of ocean water has been historically the standard for measurement of oxygen isotope. So VSMAO is kind of a cool thing to know and tell. All right. So what's the takeaway? What's the takeaway from oxygen isotope chemistry? Here it is. It turns out that every rock, every sample you take from a rock on Earth and you plot it in this oxygen isotope diagram, every sample falls on a line called the terrestrial fractionation line. And again, then maybe that makes sense because, again, the Earth started with these basic ratios, a basic amount of these 3 oxygen isotopes. There's no half-life involved. And so the only way they change is if they get heated and melted and sort of rearranged in their proportions. And consequently, the rearranged proportions are going to just be on the line. So every Earth and Moon rock falls on this terrestrial fractionation line. Now here's the power. Here's the power of isotopic chemistry. And the amazing thing I want you to know about isotopic chemistry is that when we measure the isotopic ratios, the oxygen isotopes in meteorites, we see that meteorites don't match the oxygen isotope ratios for the Earth. And this is how we know that meteorites come from different places in our solar system. And the changes in the oxygen isotopes are related to what were the pressure and temperature and chemical conditions at the location where each of those meteorites was formed. And so oxygen isotope chemistry is an amazing way of looking back and understanding the conditions in the early solar system. So you understand why I love oxygen isotopes. But here's the kicker, and here's how this relates to the moon. We went to the moon, we brought back those samples, measured those samples in the laboratory. And you know what? Oxygen isotopes in the lunar samples also fall on the same Earth fractionation line. And now we call it the Earth-Moon fractionation line. The fact that the Earth and the Moon are matching in their oxygen isotopes is the evidence that the Earth and the Moon were born together early in the solar system. They were united. They have some common origin at the beginning of the solar system. So you see how this oxygen isotope result is an incredibly powerful outcome of the Apollo missions of the Apollo era, telling us about the early solar system and how we got our moon. So our facts about the moon, the different densities, how the moon orbits around in the ecliptic plane, not around the Earth's equator, and these oxygen isotope results that the Earth and the moon must have been born together somehow, but they're not identical twins. They're fraternal twins or siblings, but related to a common origin. So now we have 5 facts about the moon that theories have to explain. And it turns out in looking at these available theories and these new facts that became available, the new facts basically still contradicted or even made worse our conclusions or any possibility of any one of these hypotheses being correct. So we were still left over with a mystery about where the moon came from, even after we brought the samples back. But it took a little bit of thinking. And that bit of thinking was really to go back to square one, to go back to the beginning and think about this disk of gas and dust and early planetesimals forming in the beginning of our solar system. And could we make sense of the new data from the Apollo program? So we're going to recall that our solar system began with this disk of gas and dust collapsing in our region of the galaxy. The dust grains beginning to coagulate, coming together, growing larger and larger like giant cosmic dust bunnies. Those dust grains clumping into planetesimals. And we have samples of these. We have clumps of these early planetesimals. The carbonaceous chondrite meteorites are those samples of the earliest solids in our solar system growing out of this material. And so we have in our solar system and in our planetary neighborhood, all these planetesimals coming together, trying to coalesce into planets. And we're going to focus on this late stage of planetesimal accretion, where these leftover planetesimals are colliding with each other, sort of duking it out to try to see what will survive, sort of survival of the fittest. And this occurs at this stage in planetary formation we call after the T-Tauri phase, when the early sun, the strong solar wind from the early sun, has blown out all of the gas. And we're really dealing with just the solid planetesimals left behind. So it's these solid planetesimals left behind that are collisionally interacting with each other that creates what I call cosmic mayhem, sort of a cosmic mayhem among all these leftover planetesimals. So last class, Julien showed you a simulation of some of these early planetesimal accretion. I wanted to put here the reference again for that simulation to give due credit to the authors. And here is that simulation where we're looking at the distance from the sun in AU. Of course, the Earth is right around here at 1 AU. This is the eccentricity of the orbit, or how circular or non-circular those orbits are. This is the inclination, the tilt of the orbits. And then at the top, you see the size of each of the particles is basically reminding you how large these particles are growing. So we saw that simulation before. We can now look at this in a little more of a snapshot way and a sort of an earlier generation set of models for the early solar system forming basically just in the few tens of millions of years after the solar system started forming. So we begin with lots and lots of planetesimals. They interact, collide with each other, coalesce. We get fewer and fewer planetesimals, but we get as they coalesce, some of them grow in mass. Again, distance from the sun, where they're located. And as time goes on, we get to these later stages. We see fewer and fewer planetesimals because they've been gathered in, swallowed up by some of the larger objects, or they've been flung out of the solar system because they interact with Jupiter or one of these other large bodies. And really, it's just a process by which the biggest bullies eventually win. The biggest objects effectively can absorb or withstand collisions with the remaining particles and sort of assimilate the ongoing particles. But the important point here is that even some of the bullies take hits. So as we get to the end stage of this process, the big guys are going to win, but the little guys, as they are not going to give up without a fight. And so this is really what we think now formed the basis of how we got the moon. And that is early on, at this late stage in planetary formation, in the vicinity of the Earth, there were sort of dueling planetesimals for who was going to dominate at 1 AU. And the Earth was the largest of these objects, but there was still at least one or more other leftover planetesimals, sort of a Mars-sized planetesimal is usually the thought, and that the moon was formed by the impact of one of these other late-stage planetesimals, which we know were around, and maybe one of those struck the Earth, splashed material off, and formed the moon. And so this is this giant impact hypothesis where we have a proto-Earth, an Earth that's just about ready to be finished forming, and then this mythical body, or has this mythical name named Theia. I don't particularly subscribe to that naming of it, but that name is out there. And so it's sort of another body that wanted to be a planet but didn't survive and ended up colliding with the Earth as an outcome, being the formation of the moon. Okay, so I want to ask a question, remembering the early stages of planetesimal formation, that the Earth is forming, it's hot, and so the iron in the elements, of all the elements that are present in the Earth, iron being one of the heaviest, is able to sink to the core. And so, just stop and think, what outcome might you expect if we have a giant collision, sort of out there, as you see there on the left, if you have a giant collision that occurs after much of the iron of the Earth has formed to the core, what outcome might you expect if the young Earth had started to become differentiated prior to a giant impact splashing material off. And I think it's important to realize that a giant impact didn't necessarily have to be a head-on collision with the Earth. I mean, chances are it was more of a glancing blow, just simply because that's just among the most likely kind of collision scenarios is something that's just somehow off center. And so, if the Earth has already started differentiating to make its iron core, then anything that splashes material off is likely to be splashing more material off from the outer layers than from the core. And so this is seen in a simulation here. I'm going to pause the recording here just to get this simulation going. And here we are. So this is a simulation performed by Dr. Robin Canup at the Southwest Research Institute in Boulder. And this is a simulation of basically a Mars-sized planetesimal impacting the proto-Earth. And if I get it to run, there we go. And you can see that in this simulation, most of the material is splashed off from the outer layers of the Earth. But it's quite an amazing mixing scenario after that impact, where, as you'll see as it runs, there's a mix of material that's left over that manages to find itself in orbit around the Earth that eventually can coalesce into the moon. But you see that the process of the impact and all of the debris ends up being quite a mixture between the Earth and the moon. So I'm going to just stay silent here and let it run again. It's a different version. So here's our just some snapshots from the simulation there by Dr. Canup, and sort of a time series step of this kind of animation. So we call this hypothesis the giant impact hypothesis. And we can see, how does the giant impact hypothesis, how does it mesh with the basic facts that we have about the moon? So the first thing that a theory about the formation of the moon needs to explain is the differences in densities between the Earth and the moon. And so it seems to make sense that if, as you see in the diagram, if the Earth was struck by a large planetesimal, a giant impact, and that impact splashed material off the crust of the Earth, then naturally the density of the moon would be lower than the overall density of the Earth, because there's no iron, or very little iron, that gets into the moon. Most of the iron was in the core of the Earth, and that wasn't the material that got splashed off. So far, so good. The second and third facts about the moon is its orbit. The moon is orbiting in the basically the same plane as the Earth, going around the sun, not around Earth's equator. And it makes sense that if there's another planetesimal out there that strikes the Earth, that planetesimal is going to be in the plane of the solar system. And so when it strikes the Earth, and all the angular momentum of the material that gets splashed off is going to be have as a resident plane the plane of the ecliptic. And so the material that gets splashed off of the Earth is going to be finding itself spinning around and orbiting around more closely to the ecliptic plane where the impacting body came from than around the Earth's equator. And so a giant impact might very naturally create a moon or material orbiting around the Earth that is closer to the ecliptic plane than the Earth's equatorial plane. Finally, we have the Apollo results that the moon has the same isotopic chemistry, this Earth and moon having a common origin at some point in the solar system, makes sense because we saw in those simulations, those simulation models, how much mixing was going on between the impacting body and the upper layers of the Earth. And so those were thoroughly mixed, and would make sense that we would see matching isotopic chemistry between the Earth and the moon. And then, so check mark for item number 4. One more to go, and that is that the moon matches the Earth's crust. The moon is iron poor. So again, a glancing blow that misses the iron that had already coalesced into the core of the Earth makes sense for forming the moon and forming an iron poor moon. And so the giant impact hypothesis, which is well established, well accepted today, is how we think the moon formed. And interestingly, as we get more and more detailed chemistry, chemical analysis, isotopic analysis of the lunar samples that are continue to be studied, we're starting to find small differences between the Earth and the moon that may be telltale signatures of that there was some uniqueness, some unique identity to the impacting body that hit the Earth. So there's a line, an area of ongoing research. All right. So to wrap up, I want to begin or try to help you appreciate things about the moon that give you a cosmic perspective that you not only can appreciate now, but we hope you'll appreciate forever. And there are so many things about this class that we hope that you will carry with you, not just to the end of the semester, but everywhere. For the rest of your life, you'll be thinking with a more cosmic perspective as a result of this semester's odyssey, which has been an odyssey in more ways than we thought. All right. So think about this photo and think about what time of day this photo must have been taken. Is it obvious to you when this photo was taken? Is it obvious that this had to be either sunrise or sunset? And in fact, this picture was taken near sunrise. And how do we know that? Well, let's think about that for a minute. When you look at the moon, and you can think about it in this picture, where's the sun? Where's the sun relative to the camera lens? Where's the sun? Well, this leads, or these questions lead to a rule, simple rule, that says when you see the moon in the sky, pay attention and think about where is the sun? Where is the sun? So why have this rule? Why is this rule important to having a cosmic perspective? Well, it has to do with the phases of the moon. And you're probably quite familiar with diagrams like this for phases of the moon. And maybe it's intuitively obvious, and you've known this since junior high school, exactly how the phases of the moon work. But if you don't have this ingrained in your head and automatically thinking about it and able to visualize it, now's the time. This is something we'd like you to come away with. So try this for yourself. You can demonstrate this to yourself. When you go outside and you see a crescent moon, stop and say, where's the sun? Figure out where the sun is. It probably is just set in the west or it's rising in the east, depending whether it's a waxing crescent or waning crescent. But if you see a crescent moon and kind of visualize where the sun is, you will always notice that the crescent moon, that the angle between the crescent moon and the sun is a narrow angle or an acute angle. And it makes sense as to why you're seeing a crescent, because the moon is just barely angling its way away from the sun. And maybe even more obvious is when you see a quarter moon and then you stop and say, where's the sun? Oh, it's 90 degrees away. That's because a quarter moon, the reason why we see a quarter moon or a half moon is this exact 90-degree angle. And so you see that the phase of the moon, grows as the angle increases. It makes perfect sense. I hope you've thought about it before, but think about it now. And as the angle becomes larger and larger between the Earth, between the moon and the sun, with the Earth at the center, we get to what's called the gibbous phase. And here I just remind you, I think it's obvious, but it's amazing how many times I've been asked this question. And if it's not obvious, it should be now. Is that everyone on Earth, when you're looking at the moon, no matter where you are on Earth, if you can see the moon, everyone who sees the moon is seeing the same phase of the moon. And so maybe right now you're separated from a family or friends or significant others. But if you're talking with them and you're looking up at the moon, you can look up and see the same moon at the same time, no matter where you are on Earth. And that's a pretty uniting statement. But that's not my point, exact point for why and how the moon gives you a cosmic perspective. I'm coming to that. So finally, maybe it's obvious that the reason why you get a full moon is because the sun and the earth are on opposite sides. And that's when you get the full moon. So when it's this case, the sun has to either be rising or setting if you're seeing the full moon rising or setting. So the full moon always has to be opposite the sun. And that means if you go out at midnight and see the full moon, you'll see the full moon, as high in the sky or as high in the sky as it can get, because the sun is directly underneath your feet at the time of the full moon. All right. So here's the takeaway. When you see the moon and the sun and think about where is the sun, you're getting in mind that relative orientation between the earth, moon, and sun. And therefore, you're getting in mind this dimensionality, this cosmic perspective that you are on a planet with the moon orbiting a star. And you can grasp that amazing concept, which isn't obvious in day-to-day life, but it's true. But you can remind yourself, reground yourself about this cosmic perspective anytime you see the moon and think about where's the sun and think about the orientation. And that's how you remind yourself of the dimensionality of the cosmos and your place in it. And that's a perspective that you can carry with you forever. So with that, wraps up our lecture on the origin of the moon. I'm going to put up here for just a short bit the learning objectives that we started out with in this lecture. They're sort of rephrased in the form of questions. And you can stop and look at those questions and see if they, and test yourself to see whether you grasped an answer to these questions. And if not, go back to the beginning, take another look through the video, and I'll see you in class.